Today we're going to talk about properties of logarithms. So we want to learn something called the change of base formula. This is a very handy thing. So it says let a, b, and x be positive real numbers such that a is not equal to 1 and b is not equal to 1. Then the log base a of x can be converted to a different base using any of the following formulas. The log base a of x equals the log base b of x divided by the log base b of a. The log base a of x can equal the log base 10 of x divided by the log base 10 of a. The log base a of x can equal the natural log of x divided by the natural log of a. So if you'll notice, all you're going to do is take, you don't use this one so often, but these you use more often. If I want to convert the base, I can just use my log key, my plain old log key, log, that's the log base 10. So I can do the log 10 divided by the log of a, and that will give me the same answer as if I do the natural log of a over the natural log of x, which is the same answer as the log base a of x. Okay, so let's me convert, and if I have a calculator that will not do anything other than the log base 10 or the natural log, then I can use it to find those answers. So, for example, the log base 4 of 25. I may not have a calculator that will do that. I may not be able to figure it out in my head. But what I can do is if I've got a calculator that has a natural log on it, I can do the natural log of 25 divided by the natural log of 4. And so I go ahead and push the natural log of 25, close the parentheses, divided by the natural log of 4, close the parentheses, enter, and I get 2.3219. Okay, let's change this color here. All right, now I could also do just log of 25 divided by log of 4. So log 25 divided by log of 4, make sure you close the parentheses each time, comes out to be 2.3219. Okay, so now all these numbers are different. This number and this number are not the same, this number and this number are not the same, but when you divide them it comes out to be the same. All right, so I'm going to let you pause the video here really quick. And I'll let you figure out what the log base 3 of 17 is, and then you can jump back on here and compare it with what I've got. Do it both ways, by the way, just to confirm that they're the same. All right, so pause the video now. Okay, so if you're going to do the natural log of 17 divided by natural log of 3, comes out to be about 2.5789. If I went ahead and did the log of 17 divided by the log of 3, it's like math magic, it comes out to be 2.5789. Okay, changing bases using natural logs. So this is pretty much what I just did here. I just did it, it said use, okay. So I wasn't paying real close attention here. This right here should actually go right here. And then I can move this up here, this right here. Should go right there. And I can take this and move it up here. Helps to read the directions. Okay, so example 1 and example 2, we did them together. No big deal, they're both done. All right, so properties of logarithms. Let a and b be positive real numbers such that a is not equal to 1, and let n be a real number. If u and v are positive real numbers, then the following properties are true. Okay, these are things you might want to write down for notes because you're going to use these a lot. The product property. The The log base a of u times v is the log base a of u plus the log base a of v. And it works the same for natural logs. Natural log of u times v is the natural log of u plus the natural log of v. The quotient property, the log base a of u divided by v, is the log base a of u minus the log base a of v, or it's the same with the natural logs. And finally, the power property. The log base a of u to the n power is n times the log base a of u. So if I've got an exponent up here, I can take it out and move it out in front, and that's the same thing. And it works the same for natural logs. I would make sure that I had this written down somewhere. Okay? So write each logarithm in terms of natural log of 2 and natural log of 3. All right, well, here's what I know. I know that the natural log of 6 is the natural log of 3 times 2. So this is the natural log of 3 plus the natural log of 2. And you can actually do that on your calculator to kind of convince yourself that that's true. All right, with the quotient property, so I would rewrite this. This is the natural log of 2 over 3 to the third power. Now, why did I do that? Well, it said I needed to change this to the natural log of 2 and natural log of 3. And so 27 is 3 to the third power, so now I can do that. So this is going to equal the natural log of 2 minus the natural log of 3, but I've got an exponent, so I'm going to pull that exponent out here in front. It's going to be like that. Natural log of 2 minus 3 times the natural log of 3. And again, you can do this on your calculator, you can do this on your calculator and confirm that those are the same numbers. Use properties of logarithms to verify that the negative log base 10 of 1 over 100 is equal to the log base 10 of 100. Okay, so if I think about this, remember logs are exponents, right? So I want to know what this is. So 10 to the y power is 100, and so y is going to come out to be 2. So this whole side right here is going to be 2. All right, over here, the negative log base 10. So let's just save that negative out here. Let's just look at this part right here, and we'll do the same thing we did here, right? So we're going to go 10 to the y power is going to equal 1/100th. Okay, so it's going to be a negative exponent. So y is going to come out to be negative 2, because a negative flips it over, and then 10 squared is 100, okay? And then I've still got this negative out here in front. So this is negative 2, which, guess what? That's positive 2. So those are the same thing. We verify that those are the same thing. Okay, now here's an object that here's something you're going to have to be able to do on an exam. You're going to have to be able to expand an expression. So here we go. What I want to do is I want to break this up into as many terms as I can. So this is equal to the log base 4 of 5 plus 3 times the log base 4 of x plus the log base 4 of y. So I just used all my properties here. My multiplication property, my product property, and my exponential, or my, my exponent property. So I've expanded this as far as it can go. It won't go any further. Now, here's a problem that people make a lot. They leave for some reason, they leave constants with some other variable. I can break that apart. This is 3 different terms, 5, x cubed, and y. So I should have 3 terms over here. And they're all being multiplied, so they all should be added. All right, so let's look at the next one. Expand the natural log of the square root of 3x minus 5 over 7. Okay, so this is going to be, this is 3x minus 5 to the 1/2 power, so this is going to equal 1/2 the natural log of 3x minus 5 divided by, so that means minus the natural log of 7. Now, here's where people make mistakes. They try to break this up, and you can't. You can't break up subtraction or addition. You can only break up multiplication and division. Okay, so this is as far as I can go. This 1/2 applies to all this stuff here. All right, so there's my problem. Now, here's a nice one. The natural log of 3x squared y to the 4th square root of z plus 2 divided by 8w to the 6th power v to the 3rd power. Okay, so I got a lot of stuff here. This looks really scary, but it's really not. So, anything in the numerator gets added, anything in the denominator gets subtracted. So here we go. Natural log of 3 plus 2 times the natural log of x, because it's x squared, right? Plus 4 times the natural log of y, because it's y to the 4th, plus square root is a 1/2 power, natural log of z plus 2, and that I can't break up because it's addition. Now I'm going to subtract the natural log of 8. I'm going to subtract 6 times the natural log of w, and I'm going to subtract 3 times the natural log of v. Now, I get asked a lot, Mr. Lippy, you said that anytime you multiply, you add these things together, and that's true. I could do this differently. I could write this, if I wanted to, as the natural log of 3 plus 2 natural log of x plus 4 natural log of y plus 1/2 natural log of z plus 2. Nobody really has any trouble with that. Minus, and then I can put all this in parentheses if I wanted, natural log of 8 plus 6 natural log of w plus 3 natural log of v. Okay, so I could do that because I'd be subtracting all this stuff, and if you think about it, basically what I would be doing is taking this negative and distributing it in here, and so all these would be negative anyway. So I don't care which way you write it. You can write it like this, you can write it like this. They're both right. But you better have, if you're going to do this, you better have those parentheses around the outside because you're subtracting all of it. Okay, use properties of logarithms to condense each expression. Okay, so what does this mean? Well, we're log base 10, so this is all going to be log base 10. And then inside there I'm going to have x to the 1/2, so that's the square root of x. Plus means times x plus 1 to the 3rd power. And I'm done. You might pause this and do this one on your own, and then jump back on here and see what you get. So I'll give you a second to pause it. Okay, let's find a different color here. So this one is natural log, so I'm going to have natural log. I've got x plus 2 to the 2nd power. And then this means divide by just x. There you go, you're done. All right, this one's a little bit trickier. I got log base 2, so this is going to equal log base 2. Now what's going to go inside? So it's all of this stuff to the 1/3. So it's going to be a cube root. And then it's going to be x times x minus 4. Just like that. Okay. You got to make sure everything's under the cube root because it's 1/3 and it's all of that stuff that it's 1/3 of. Okay. Whoops. All right, this table shows the mean distance x from the sun and the period y, the time it takes the planet to orbit the sun for each of the 6 planets that are closest to the sun. In the table, the mean distance is given in astronomical units, where Earth's mean distance is defined as 1. So the period is given in years. The points on the table are plotted in a picture below. Find an equation that relates x and y. All right. So, if you try to just graph these, where you have the mean distance on the x-axis and the period in the y-axis, you get something that looks like this. So it'd be distance, and you get years, or actually we'll say period. All right, and when you get you get this stuff down here, 1, 2, 3, 4. That's supposed to be 4 dots. And then it starts to do this. So that's exponential. It's curved. Okay. Now, it's not very clear how the equation relates an x and a y. So, but here's what you can do, is you can take the natural log of all the x and y values in this graph. Okay? So if I do that, if I take the natural log of 0.387, I get negative 0.949. And Venus, I get negative 0.324. Earth, I get 0, because the natural log of 1 is 0. Then I get 0.421. I get 1.649. And I get 2.255. And then if I take the natural log of the periods, I get negative 1.423, negative 0.486. I get 0 again, 0.632. 2.473, and finally you get 3.383. 3.383. And then you find something interesting happens, because I don't know how that happened. If you regraph those, you get a straight line. There's only 2 down here. You get a straight line like that. And we can easily find the equation of a line. So we can say, well, y equals mx plus b. And we can find the slope by taking 2 points and doing the y2 minus y1 over x2 minus x1 thing. That'll give us the slope. So if we choose Mars and Earth, then we get 0.632 minus 0 over 0.421 minus 0. And that comes out to be dang near exactly 1.5. And then we know that the y-intercept of this is 0. So we get an equation, y equals 3/2 x. Now that's in logarithms, so we had already taken the logs of these, so we need to convert this equation. We're going to take the natural log of y minus or equals the natural log of 3/2 x, and that comes out to be natural log of y equals 3 3/2 the natural log of x. Okay, so we got to be careful here. This is little x and little y. This was actually a capital X and a capital Y. Okay, the x and y go here, and this equation, this is little y and little x. This is big Y and big X. So this is actually the equation. Oops. This is actually the equation here that goes with this stuff here. And occasionally in scientific endeavors, this ends up making, by doing this, by taking the logs, you find patterns that you wouldn't have found by not doing that. Okay. Slide rule. Okay, it's based on a logarithmic system. If you've ever seen the movie Apollo 13, in Apollo 13 you see a lot of nerdy guys with black glasses and tape in the middle and pocket protectors, and they're using slide rules, which they have in their pockets, as calculators in order to save the men that were on Apollo 13 that had an accident, and they didn't think they were going to bring those guys home. But they had to do a whole bunch of extremely accurate, extremely difficult mathematical calculations, and since this bad boy didn't exist in those days, they were using slide rules. That is a movie that I highly recommend that you watch. It's got Kevin Costner in it. It's a very, very good movie. Okay. So here's your assignment. And there's a couple pages. They're not super clear, so I posted the actual photos in Google Classroom for you. So have a great day.